thank you for the introduction. And today I want to present what we have done so far at CERN in the context of enabling root computation, SYCL computation within root R data frame. The talk will cover first a bit of background. I will talk about the analysis workflow within high energy physics applications. I will then introduce a bit more in detail some core operations before coming to the main topic, Gem Vector X. And last, I will talk about two real-world test cases we have been tackling before concluding. So at CERN, as you may know already, we host the world's largest particle collider, the HL-LHC, which you can see in the picture on the right. Here, beams of particles of protons mainly are accelerated and made collide in order to discover the fundamentals of our universe. And such collisions are stored in a digitalized format, which is referred to event. And every event is made of a set of four-dimensional particles in the time space. Of course, the LHC is operating since 2011, so we have a large amount of data, petabytes of data, that needs to be analyzed efficiently. And to do this, the Root library comes into play. Root is an open source C++ framework for high energy physics analysis. And within Root, our data frame is our user-friendly interface, the most used by the physicists for analyzing their data. Here, data are intended in a columnar format. Each row represents an event, and each event's property is stored in a column. And events, as I already mentioned, typically involve four-dimensional vectors, so-called Lorentz vector, which represents objects in the time space. So the figure on the right, for example, shows an histogram produced with Root by the Atlas collaboration in the context of the well-known Higgs boson discovery, for which, of course, Root played an important role. Let me now introduce a typical workflow of a high energy physics analysis. So what we have to do is first, of course, reading data from disk. These data are usually stored in a compressed format, so we have to decompress such data. Usually we read bunches of data, which we call bulks. We then filter those events which are not relevant for the analysis. And we may also want to define some derived quantities. Usually such operations are iterated, so we repeat more filtering, more defined operations, depending on what the physicist wants to achieve. And last, we aggregate results, usually producing a histogram. How do we do this within our data frame? In this code snippet, you can see a very simple workflow providing a quick analysis, a simple analysis. So in line code 1, we first read the dataset from disk. In line code 2, we define a function invariant mass, which takes as inputs four doubles for scalar values. We then define in line 3 a four-dimensional vector with respect to a given coordinate system. And in line 4, we exploit such a root object to get out, to compute the invariant mass of this particle. In lines 6 and 7, we have the definition of the RDF workflow. So we first we first have a filter action. We filter out, we leave out all those events for which the x-coordinate is null. So we want to keep only those events for which x is non-zero. We then define for these events that pass the filter a new quantity, m, using the invariant mass function. And this function will take into account as inputs the columns x, y, z, and e, which are defined in the dataset, of course. And last, we aggregate results computing a one-dimensional histogram over the quantity we have just defined, the invariant mass. And last, we withdraw such results. We draw the histogram. So we have a single loop over all the events, and the events, as I mentioned, are grouped in bulks. And the actions here, we have a filter, we have a define, and last we have a 1D histogram are applied in sequence for every bulk of event. And it's important to notice that the users here have a large flexibility in what they want to achieve. Indeed, they can provide to the define action a function that they write themselves. However, hard data frame has also some limitations. Indeed, it supports multi-threading and distributed execution. However, it does not support, for example, execution on GPUs. So indeed, we want to increase heterogeneity in our computing facilities in order to improve performance. And this is our goal. And we start tackling the histogramming action and the define action we just talked about. So even if it is not the main focus of this talk, let me briefly discuss the GPU histogram action. If you want to know more about this, we have a paper from last year, which is cited in the footnote. The figure here describes the workflow of our data frame performing a histogram action on the GPU, how it is now implemented in our R&D branches. So first, we trigger the event loop. We load the bulk in memory. Such bulk is then transferred to the GPU, where the computation happens. So we find the bin to fill within the histogram based on the value of the coordinate. We update such bin, and we also update the statistics, the mean, standard deviation, higher order momenta, before copy back the result to the CPU. Let me introduce you some numerical results. So here in the figure on the right, you see the total time for the execution of such operation plotted with respect to the number of events. So here we have 4 different use cases where the number of events goes from 50 million to 1 billion. And we compare 5 different approaches. Plain CUDA versus 2 different implementation of SYCL, so DPC++ and adaptive CPP. And we also compare 2 different memory access strategies, the device device pointers and the buffers. The colors of the histograms here represent different operations. In brown, we have memory transfers, and in red, we also have some memory operations here representing mallocs and frees. So what we can see, this is a large amount of the total time of execution. We can achieve a speed up with respect to a multi-threaded CPU execution that is about 2 times for DPC++ and 1.5 times for adaptive CPP. And this is for the largest use case, the 1 billion event use case. And the speed up is, of course, not great. And this is indeed because memory operations are too heavy with respect to the computational intensity of the kernel for computing a histogram. So the idea is to increase this computational intensity, of course, by offloading also defined actions. And here comes into play the GenVector package of root, which is a large package, about 11K lines, enabling fundamental operations with 2, 3, and 4-dimensional physical vectors, which can be expressed in different coordinate systems, Cartesian, polar, cylindrical, and more. The users can also specify the underlying scalar type, namely single or double precision. And we also have more advanced operations such as rotations, Lorentz and Poincaré transformations. So the goal here, what we have done, is to move from GenVector to GenVector X, where the X stands for accelerated. And we have done this in order to tackle parallel execution on NVIDIA GPUs via plain CUDA and on other backends via SYCL. Of course, while retaining performance and a user-friendly API. So GenVector X in detail is a library of external data structures and objects. And it is compiled for CPU, CUDA, and SYCL backends, as I already mentioned. In this code snippet, you see an example of a class definition within GenVector X. So in line 2, you see that we have a namespace that is macro defined. This macro is defined at compile time. And for example, it is math for CPU, math SYCL for SYCL, math CUDA for CUDA, and so on. And in this example, we are defining a class representing a 4-dimensional vector with respect to the coordinate system pt, eta, phi, e. We have in line 6 the default constructor. In line 8, we have the magnitude of momentum, which we cut out because of space constraints. And in line 9, we have the definition of the invariant mass. Here we are using a square root whose scope is defined at compile time according to the backend we are trying to tackle. For example, we will pick SYCL square root if we are tackling, if we are targeting the SYCL backend. Such objects, such classes can be used within kernels, of course. Here we have 2 examples of kernel definition, a SYCL kernel versus a CUDA kernel. Both computing invariant masses for two sequences of four-dimensional vectors. And what I want to point out is that here we are able to, using the API provided by JVectorX for both SYCL kernel and CUDA kernels. So this allows users, for example, to write the kernel the same way they would do for a CPU computation. And this is very flexible. Let me briefly talk about code similarity. Indeed, we have evaluated such quantity on a set of platforms, CUDA, SYCL, and CPU. Of course, code similarity is a measure of similarity between code bases, whose value ranges from 0 to 1, where 0 means completely orthogonal and 1 means equal. And as we see in the table, both CUDA and SYCL have a very high similarity value with respect to the CPU if we evaluate such quantity, taking into account the invariant masses problem. Meaning that the code base is highly maintainable, highly sustainable. However, we have to take into account that CUDA can only tackle NVIDIA GPUs, while SYCL can tackle a much larger set of backends. Let's move to numerical experiments. So here we have 4 computing environments. 3 NVIDIA GPUs, the first one being a gaming GPU, the other 2 being data center GPUs. And we also have an AMD GPU, which is also a data center one. And what we do is, again, to compare 2 different memory strategies for SYCL, buffer versus device pointers. And we also compare 2 SYCL implementations, Intel One API or DPC++ versus adaptive CPP. This first numerical example shows the scaling of the kernel for computing the invariant masses. So we show the runtime in the y-axis versus the number of particles on the x-axis. And again, we compare the 5 approaches we discussed previously. So what we can see is that we have a slight gap between One API and adaptive CPP on the NVIDIA GPUs, where One API can perform very similarly to NVIDIA CUDA. And this gap is filled if we take into account the AMD card, which is the figure on the bottom right. Just a disclaimer: these results do not show timings for memory transfers. In this second test case, we take into account the total time for execution, so we take into account memory transfer as well. These results, these figures shows the total time against the number of particles. So for each figure, we have 4 different test cases, 4 different number of particles. And we don't take into account here the AMD card because we used NVIDIA Nsight for producing such figures. And again, the coloring refers to the different operation type. In brown, we have memory transfers, and again, in red, we have other memory operations such as mallocs, freeze, and so on. And we can see again that this is the largest amount of the execution time. So the Invariant masses alone is not enough to fully exploit the GPU capability again. And in order to overcome this issue, we have implemented and designed, fused, define, and histogram in action. So the histogramming class is templated over a define operator whose signature is fixed, but the operator itself can be provided by the user. And we have carried out a primary investigation, numerical investigation, taking into account two real-world use cases, which I will now introduce, the D-Muon analysis and the folded W analysis. So for what concerns the D-Muon analysis, the goal here is to calculate invariant mass for all the events which have exactly two muons with opposite charge. Figure on the right shows the workflow. So we first load the events from a disk. We filter out all the irrelevant events on the CPU in order to avoid unnecessary memory transfers. So after we have only the good events, we pack them in a bulk and we transfer such bulk to the GPU, where we can compute then invariant masses and we can fill the histogram. So here, in order to have an idea of the computational intensity of this test case, we transfer 8 doubles, so two 4-dimensional particles, to fill a bin in a single histogram. Now let's talk about the folded W analysis. In this case, the goal is to calculate forward folding and invariant mass, again on a subset of events. So again, we load in memory the data and we filter out on the CPU all those events which are no good. So then we pack this good data in bulks and we transfer such bulks to the GPU, where we compute the forward fold, we compute the invariant mass, and we fill the histogram. However, the forward fold here is variable dependent. So it takes two variables in inputs, the scale and the resolution, each of which in this test case might take 100 values. So we have in total 10K combinations. So we have to compute the forward fold 10K times, and the same for the invariant masses, and we have to fill 10K histograms. So for this test case, the computational intensity is much higher. This is clear. Let's now briefly discuss numerical results. In this table, we can see the number of events for the two test cases, which is 24 million for the D-Muon analysis and 100K for the folded W analysis. We also have the speed up of our multi-threaded CPU execution, which is 2.6 for the D-Muon analysis and 95 for the folded W analysis. And last, we also have the percentage of time spent in data transfers. Of course, these preliminary results, again, tells us that the performance is heavily test case dependent, and indeed in the case of folded W analysis, in which the computational intensity is much higher, we have a much higher speed up. And yeah, just to mention this, for these results, for these numbers, we use device pointers instead of buffers, and we use the DPC++ compiler. So As a disclaimer, just take into account the fact that here we are not counting the overhead caused by the RDF bulk API. Indeed, what we are working on at the moment is the integration within RDF. In this code snippet, you can see what we want to achieve at some point. Again, we have a small workflow in which we first read from data from disk the data. We then define a filter action, and then we define we use the diffuse, the define, and histogram in action, providing an external SYCL device function. And in this way, the users will be able to define the function they really need to in order to provide their analysis. So this maintains the same flexibility that RDF already provides. However, in order to achieve this, we are missing, as I already mentioned, a full integration with RDF, and we need to integrate as well with the SYCL-enable Cling, which is a root just-in-time compiler, which is also developed within the scope of this project by Devajit, a member of our root team. So let me sum up what we did so far. We detailed the migration to both SYCL and CUDA of gem vector and histogram action within RDF. We evaluated the divergence of such code bases. We have showed empirically, of course, the performance portability, and we provided evidence of a significant performance gain for suitable test cases when we combine define and histogram actions. What needs to be done in the future is to complete the integration within root with RDF and with the SYCL-enable Cling. We want to carry out more test cases using other platforms, for example, Intel GPUs and RISC-V, of course. And we have in plan to extend GemVectorX to tackle even more complex high-energy physics analysis. So if you want to know more about this, we have you have here the link to the GitHub branch containing the code used to produce the results you have seen. And we also have a paper here. You have the preprint, which will appear on the Journal of Physics. This is it. Thank you for listening so far.
Thank you very much.